Hello everyone, welcome to what will be pre-lecture 17, and we're going to be covering doing an introduction to buffers in this pre-lecture. So what is a buffer? Chemically speaking, it is a conjugate acid-base pair that makes a buffered solution, and the characteristic most commonly given to buffer solutions is that they are resistant to changes in pH when we add any sort of acid or base to them. And so typically that means we have some sort of weak acid like acetic acid shown here, and some sort of weak base or its conjugate base, which is a weak base, sodium acetate. And a key point there is that we cannot make buffers with strong acids or strong bases. So for example, if we had just water and sodium hydroxide, which is technically a conjugate acid-base pair, we wouldn't have a buffer, we would just have a basic solution, okay? If we think about what these look like, if we have a solution that is unbuffered and a solution that is buffered with the presence of a pH indicator, so pH indicators change color when we have changes in pH. If we were to add a small amount of acid to the solution on the left here, we would see a change in color, indicating that we have a change in pH, whereas with our buffered solution, we don't see a change in pH. In reality, we change the pH, but only very slightly. And again, that is showing us this resistance to a change in pH, okay? Another way we can visualize that is, say we have continuing the example, a weak acid, an acetic acid, and a weak base in its conjugate base, acetate. If we were to add acid to that solution, that acid would react with our base, right? If we add acid, it is going to react with the base, and it will form more of our weak acid. Whereas if we add base in the form of hydroxide, that is going to react with our acid to form more of our conjugate base. So you can kind of see the cycle that we create here. And what this also means for us, or another way we could represent that rather, is if we start with an equal amount of weak acid and weak base, we don't have to start with an equal amount, but say we do. If we were to add acid or add base, we can see how the relative proportions change, where if we basically add 1 unit of acid here, we see that our base changes by the same amount of that 1 unit going up, okay? Or I guess that was reversed here, where if we add acid, it will react with our base and make the same amount of acid. Okay, so that's just a different way to represent the same thing. And so if we are asked to calculate anything with pH related to buffers, which hint, hint, you will be asked to do that at some point, your first instinct may be to build an ice chart, because that is typically what we do when we have a weak acid or a weak base. I'm going to go through an example where I do build an ice chart, but I will tell you, you should not build an ice chart. We're going to take a shortcut here by the end of this video, and you can build an ice chart. It will get you the right answer, but it just takes a lot more work. Okay, and so I'm going to go through that work and then basically assumptions that we can make. So say we have this propionic acid and we have a certain concentration of the acid and its conjugate base, sodium propanoate. We're also given a Ka value here. So I typically tell you, write out the chemical equation. So I'm just going to call this HP to represent propionic acid, just for the sake of taking up less time, and I'm going to write sodium propanoate as, well, I'm just going to call it P- for propanoate. The sodium is just going to be a spectator, so I'm just not actually going to include it in our reaction. I'm just going to say, let's start with propionic acid, say that it reacts with water, which is of course pure liquid, and that would be in equilibrium with H3O plus aqueous and P minus aqueous, right? And again, the P- is just our propanoate, HP is our propionic acid. Okay, and we could write a Ka expression for this. So Ka is going to be equal to concentration of H3O plus times our concentration of P-. And that will be over our concentration of HP, right? So that's how we typically start. And from there, we could, of course, build our ice chart. We know water is a pure liquid, so we don't need to include that. And we are told our initial concentration of both our HP and our P-. So I am going to fill those in right now. Draw my lines in here so it's a little more clear. At this point, we have both reactants and products present. So we could solve for Q and determine which way our reaction will go. Another thing we could do is realize that one of our products, H3O plus, has a concentration of 0, and we should hopefully know that it's not actually 0. If this is pure water, it would be 1.0 times 10 to the negative 7th, but it's very small. And so I'm going to make what I think is a reasonable assumption that our reaction is going to lose reactant and gain product. So if we think about our change line, it would be minus X on our reactant side plus X on our product side. And then if we combine those terms, 0.0500 minus X and 0.0450 plus X, we should end up with our completed ice chart. And so now we can take what is in this equilibrium row and plug it into our Ka expression. And so that's what I'm going to do down here. Our Ka is equal to 1.3 times 10 to the negative 5th, which just get from right there. And that is going to be equal to our concentration of H3O plus, we said, is X. Concentration of P- is 0.0450 plus X. Sorry for not the neatest writing. And then our concentration of propionic acid is 0.0500 minus X. So we can look at this, and if we just do a little quick algebra in our head, we know, oh no, we're going to have to do the quadratic equation to solve this formula. We've got a lot of x's. But we can make a simplifying assumption. If we look at our Ka value, our exponent is smaller than times 10 to the negative 4th. And so we should be able to actually cross out 2 x's this time with our x is small approximation. And just a reminder, we're able to do that because whatever x is, it's going to be relatively small compared to our initial concentration values. And so that simplifies things quite a bit to 1.3 times 10 to the negative 5th being equal to x times 0.0450 over 0.0500. Okay? And so now solving for x becomes a lot easier. We just multiply by both sides by 0.05, divide both sides by 0.045, and I got a value for x there equal to 1.44 times 10 to the negative 5th. And if we're asked to solve for pH, we can look back at our ice chart and see that our x value is equal to our concentration of hydronium. So we know if we take the negative log of our concentration of H3O plus, that should be equal to our pH. And so when I take the negative log of 1.4 times 10 to the negative 5th, I get a pH value of 4.84. Okay, so we came up with an answer there, but we had to do a fair amount of work. And so I want to say you could do this, but it will take you a lot more time than the method I'm about to show you. So let's talk about the Henderson-Hasselbalch equation. And so in the case of buffers, and I will say this a number of times, this is only true when we have a buffer solution, and our x is small approximation works, our ice chart can be simplified into a single equation. That's this equation right here. This is called the Henderson-Hasselbalch equation. And our key assumption here is that our initial concentration is going to be about equal to our final concentration for both our weak acid and our conjugate base. And ultimately, this is due to Le Chatelier's principle, right? If we have close to equal amounts of reactants and products, our reaction just isn't going to change all that much. This is ultimately derived from our Ka expression here. So if we just took a general reaction where we had basically HX and it reacts with water and it's in equilibrium with H3O plus and X minus, we could write our Ka expression for that, like there. If we rearranged it by basically getting H3O plus on its own side, so we would divide each side by X minus, multiply each side by HX. Then we took logs of both sides, and then a property of logs is you can actually split them in half. So we basically split our log terms in half. And if we multiply that then by -1, we end up with the negative log of H3O plus is equal to the negative log of Ka, which hopefully we know the negative log of H3O plus is our pH. Negative log of Ka is just pKa. And then it ends up being plus the ratio of our base over our acid, which is, of course, our Henderson-Hasselbalch equation. Okay? So we can use that, and I will tell you, I would recommend plugging in your numbers from the previous problem into the Henderson-Hasselbalch equation. Prove to yourself that even if we don't use a nice chart, we can actually end up with the same exact answer there. Okay, so that's it for this video. Hope it was informative. If you have any questions, please do let me know. Otherwise, I will see you soon.